All right, let's go over question 4. It's worked out for us so that we can kind of speed this along. It says an offshore oil well located 5 kilometers from the closest point A. So I kind of drew that. Here's my well, closest or nearest shore point A, right? That's going to be 5 kilometers. We're going to pipe oil from the well to some landing point B. That's 8 kilometers down the beach, right? So if this is A, if I go 8 kilometers this way, that's B. And basically what we want to do is we want to pipe oil from the well to some point C. So that's going to be the pipe that's underwater. And then from C on to B, that's going to be the pipe that's over land. We're trying to figure out where should we put C. Should we put it in the middle? Should we put it over here? Where should we put it? So now I got to label my picture, right? So these things in red weren't given. So you're like, where did I get them from? Well, since I'm trying to figure out where to put C, right, I got to figure out how far away from A should this landing point C be. That's an unknown distance. I decided to call it X. And now it turns out just by me labeling AC X here, everything else now gets labeled for me. So in other words, if this is X and this whole distance from A to B is 8, then CB must be 8 minus X. So that's pretty easy. And then this also is pretty easy because this is a right triangle. So the Pythagorean theorem, we have leg squared plus leg squared equals hypotenuse squared. So x squared plus 5 squared equals c squared. Solve for c, you're going to get the square root of x squared plus 25. So these variables labeled in red represent distances, right? So you have the distance underwater as radical x squared plus 25, and then the distance over land for the pipe is 8 minus x. So what do we want to do, right? We read through this, write down first, really, I should have said that I wrote this down first. Minimize cost, so I write min cost. So I have my picture, it's labeled, it's good to go. So now I need a cost function. All right, so how can I represent the cost of this pipeline? Well, they gave me some rates here. They said it's going to be $1,000,000 per kilometer to lay the pipe underwater, and it's $500,000 per kilometer to lay the pipe over land. So watch what I do here. Right, so let's think about this for a second. Let's just say, for argument's sake, that the length of this pipe, the pipe underwater, let's just say it was 2 kilometers. It's not, but let's say it was. Well, then how much would it cost to lay? And hopefully you're saying 2 million. You're like, well, how'd you figure that out? Well, if it's $1,000,000 per kilometer and you have 2 kilometers, it's just going to be 2 times 1,000,000, right? That's how you would do it. Well, all right, it's not 2 kilometers. It's this unknown radical x squared plus 25 kilometers. So the cost for laying this part of the pipe is going to be radical x squared plus 25 times 1,000,000. Now, I didn't want to write all of the zeros, so I just said, you know what, let's let C be in millions. So I could just do times 1. Likewise, right, what about the cost of this pipe? Well, the length of it is 8 minus x, and the cost is $500,000 per kilometer. So if I do 8 minus x times a half, again, because we're in millions, that would represent the cost of the pipe over land. So when I add the two together, I get the total cost of the project, right? So a neat little problem. So now what about my interval? How did I figure that out? Well, it's an interval for the variable x, and x represents this distance from A to this landing point C, right? So obviously it should make sense that you don't really want x to be negative, because if x was negative, that would imply that you're starting the pipe process by piping the oil away from B. And that, to me, doesn't seem very reasonable. So a good starting value for x would be 0. Now, what does it mean if x is equal to 0? Well, it basically means that you'd be piping straight across. So I drew, and this isn't necessary to solve the problem, but for note flow, I did it. I drew the scenario when x is 0. Basically, pipe the oil straight across. So that's the part that's underwater, and then the rest of the way, 8 kilometers over land. All right, so x can equal 0, so that's why it's closed. Now, what's the biggest x can be? Well, that would be me stretching C all the way to B. So the biggest x could be is 8, right? And that would be this scenario where we're piping the entire thing underwater, which would seem like that no way that could be the answer, right? Because it's more expensive to pipe underwater, right? So that's probably not going to be the solution to our problem, but that is the endpoint in our interval. So now if you think about it, I have a continuous function, not a polynomial, but I know it's continuous. And I go, how do you know that? Well, because there are no values in this interval that are going to break this. I'm not going to get division by 0 or anything like that. So I have a continuous function on a closed interval. That means the extreme value theorem is going to apply, right? So what does that mean? That means I'm guaranteed to have an absolute max and an absolute min, and it's going to occur either at a critical point or an endpoint, right? Those are my candidates. Well, I have my endpoints, 0 and 8. So to get the critical points, I got to take the derivative. So derivative of sum of the derivatives. The derivative of this, I have to use the chain rule. I view this as radical stuff. So the derivative would be 1 over 2 radical stuff times the derivative of stuff, times the derivative of that innermost function. The derivative of x squared plus 25 is 2x. Notice I crossed out the like factors of 2 there. Then I do plus, I have to take the derivative of this now. Now this is a constant times a function. So its derivative is just the constant times the derivative of the function. And the derivative of 8 minus x is negative 1. So this is now my derivative. I set it equal to 0. So then I would add the half over if it was me, cross multiply. I get 2x equals radical x squared plus 25. To go from here to here, it looks like I squared both sides because I want to get rid of that radical over here. Then I subtract the x squared from both sides. Then I divide by 3 on both sides. And now I plus or minus square root both sides. So now 25 is a perfect square, so the square root of that is just 5. So I cleaned it up and wrote 5 over radical 3, and I don't care about the negative because that's not in my interval 0 to 8. So what I can say now is that since c of x is continuous on the closed interval 0 to 8, the extreme value theorem applies. So let's test all our candidates. So I'm going to chuck in my endpoints 0 and 8 and my critical point 5 over radical 3. Now, where do I chuck them in? In the function we're trying to minimize, which is the cost function. If this was me, I would put this in y1 in my calculator, and then I would do y1 of 0, y1 of 8, y1 of 5 over radical 3. And when you do it, these are the values you get. And remember, they represent costs. So it's no surprise that you have an absolute max when x is 8, right? Because that would be piping everything underwater. So it's about 9,433,000. So pretty expensive. It actually turns out that the cheapest one, the minimum, is going to occur at 5 over radical 3. So what does that mean? It means there's an absolute min cost of 8.330 million when the landing point is 5 over radical 3 kilometers east of the nearest landing or shore point, I should say, right? So this distance here, if we put that 5 over radical 3 kilometers east of A, that is actually going to minimize the cost of this project, which is actually a pretty neat problem, right? 5 over radical 3, it's like 2.886 kilometers, right? So pretty neat stuff. I mean, oil company hires you, they give you these constraints on how much it costs to lay the pipeline, and you'd say, all right, this is what you got to do. If you want to build this pipeline and minimize your cost, then this is where you need to put that landing point. All right, so pretty cool real life problem we got going on there. Be good.